So high-strength Damascus steel by additive manufacturing. Does everybody know what is Damascus steel at the first place? So Damascus steel is steel that is made by folding two types of steel so that you have alternating layers of softer and harder material. That causes it to have better mechanical properties. Here, they are manufacturing Damascus-like steel by additive manufacturing, by laser additive manufacturing, that are producing three-dimensional parts from powdered metal, for powdered metal. Usually, powdered metal printing, it's done in a bed-like printer, where there is a bed of fine metal sand, and they melt it with the laser. Here they're using the nozzle type, where the metal is deposited by the carrier gas and melted at the point. So the gas is carrying the powder feed. Okay. The process, they're using the alloy of steel, which is 19 parts iron, 5 parts nickel, and 1% titanium. This makes it a miraging steel. A miraging steel is a steel that is hardened because during the heat treatment, the participants, the nickel and titanium, participate out of the metal and make little beads that cause the material to be a lot harder. In this paper, they're making the nanoparticipants by cooling the metal or stopping the printing and letting the material cool. So they're getting the nanoparticipants by cooling it, because as the temperature rises, here we can see as it's printing, they're laying down 4 layers of material, and they're pausing, because as the temperature rises of printing, the temperature of the piece goes above the martensitic temperature, the temperature at which the martensite forms. Martensite is the hard form of the steel, which is made because it's a body-centric qubit structure. That is body-centric cube.
Can you give us a little background on previous ways of making Damascus?
There are a lot of examples on YouTube, but yeah, you would weld the 2 pieces of steel together in a forge. One would be more nickel rich, and one would be normal mild steel. And you would heat it out and heat it up and fold it over itself, and do that again and again, like laminating dough for croissants.
Thank you.
I don't have any pictures ready, but yeah, it causes.
And then like hammering it like crazy, so it really vibrates together and shuffles.
Yeah, it's
a
very involved process, and takes a lot of time, and you lose a lot of material due to the scaling that forms on the outside of material. So when you're forging, air causes a scaling, and you lose that material. So that was Damascus steel. Any more questions?
Yeah.
Okay.
Because the nickel content's higher in one, and so my always understanding that it was a high carbon steel and a low carbon steel, but I've never come across in my machining world ever like dealing with Damascus. What does the high nickel content do?
well, I'm not really sure, but from the visual point, when you have a finished knife or a sword, when you etch it by acid, the pattern really pops out. You can really see a Damascus, and that's nickeled. But I'm not really sure what it's metallurgical doing in the material. I'm not really my field,
So my understanding is that much like the biological materials that you were mentioning before we got started here, the variability of different types of metals actually causes a greater strength and ability to be flexible and absorb damage. So it's all of these things have different now, I'm going to say Young's modulus, but that's only one of many things. But like all of these have like a different ability to absorb damage, and so when you mix and match them, in the same way that I was talking about the chilled plow, and in the same way that they're moving back and forth between the different heat temperatures, you get things that when the has anyone ever seen those like really messy, crazy YouTube videos of people cutting glass underwater?
Yes.
Yeah. May I make a correction? It's not the what you're referring to is stress and strain.
That's why I said Young's modulus.
Okay.
Yeah, because it like absorption in as much as that it has to do with stress and strain that vibrates through a material, which is what we call Young's modulus when we're talking about material properties in chemistry. It's like how much pressure can something take before it breaks. And so when you have like this wide variety of materials folded on each other, layered like this, it allows them to take some of the stress and strain from the material that is hard and put it into the material that isn't so hard, and so it takes up the balance. Anyway, I'll let you get back to it.
Yeah,
I have.
This is
go ahead. Slightly related question. And on the diagram you showed for the feed for the powder of the metal, well, surely having a powder going through a feed like that would have massive wear on the nozzle.
You are correct.
Yes. It's probably a specialized nozzle. These machines are millions of dollars, and it's
So they don't discuss at any point like problems with.
They don't. In this paper, there's no discussion on the wear and tear. They just stop the machine for a set period of time for the piece to cool below the martensitic temperature, and they go ahead. So they start and stop and let it just cool. But
research papers are oddly amazing at their ability to just be like, and by the way, everything that we used got destroyed while we did this research. So that's normal.
In the in the methods, they specify the equipment they use, and I looked at the machine they use for feeding, and it's the standard industrial machine for powder feeding. It's probably very expensive, but it's probably accounted for the wear of sanding with blasting with titanium sand. So anyway, just a moment, I got a little bit lost in the paper. Where was I? No. All right. So this graph pretty much tells the whole story. Different plots show the rising of temperature, which they measured by pyrograph, and as they're laying 4 layers and then waiting, we can see the 4 peaks as the 4 layers were laid, and then they shut off the machine. The first, in which there's no pausing, which went well over the temperature, the MS temperature, and there was no martensite forming and no in situ precipitation. We can see there are no visible layers, and later they're showing that it has lower mechanical properties. The others, well, they use different times of pause to let the material cool. You see each one is a bit higher and lower. The sweet spot they chose for testing was the 19 seconds of wait time and 180 seconds for testing, because they go well below the temperature and the material has a lot of time to crystallize and form the structure that is necessary and that causes the better mechanical properties. Here's the graph. They show the strain, testing of the strain. This is tested by pulling the material apart. They say the outlier here is caused by defects in the manufacturing processes, and that's very common. And the problem with additive manufacturing of metals, because there are always voids, little bubbles of air, empty space that sometimes cause failures. Another thing that's interesting is the directional strength is different. The figure A is parallel to the laser scan direction, and it's a bit higher than the other one, which is against the grain which they printed. So printing causes a buildup of structures, which when building a machine part, they alternated the direction and of scanning, so there's not buildup of crystals in one direction, so it's more uniform in strength. But here they're just printed in one way, so there's a buildup of crystals in one way, so this one is a bit lower, a bit weaker.
Can I just point out that a massive problem with additive manufacturing is inconsistent with the uniform, how the part takes stress.
Yes.
With its print orientation, this is for PLA prints in a FDM printer. Prints can be considerably weaker when pulling the layers apart compared to pulling with parallel with the part. The bit that I can see there is that the Damascus process really improves that consistency comparatively to from the no pauses. That is fantastic because of it. It's a massive problem with the manufacture of just any additive process.
Yeah. So this was the stress the tensile curve, but in this graph they show the absorbed energy, and we can clearly see that at low temperatures, which they test by doing a Sharpie impact test. Does everybody know what that is? Okay. They're just testing by hitting the piece with the big pendulum and seeing how much energy is absorbed by the piece. Here they're showing the dimensions of the tested piece, and they tested various temperatures. At low temperature, at -100 degrees, it's consistent, but at a higher degrees, higher temperatures where this type of steel is very much used, you see a great increase in strength. Since additive manufacturing of metals, there's a great use case in printing rocket engines and rocket motors, and there have been tested rocket motors made by this process. The use case is, of course, at a lot higher temperatures, so it's a very beneficial property of the material. Any questions?
Yeah, like I don't know. Correct me if I'm wrong, but I did a little look around, and when I saw that it has like on top of the high ductility means that it bends, it's flexible and all. Like I'm focusing on the nickel between the titanium and the iron. Basically, the nickel still to this day, apparently, according to Wikipedia's sources, it's still being discussed whether the electron configuration is in a certain place or not, depending on its state. So as I see it, it's so shiftly, like like nitrogen is highly kinetic. It's the perfect ligating metal to make alloys. Like it's the perfect glue for like, or like, yeah, it's a good mixing alloy to have a titanium and iron on top of being very ductile, which means it takes a lot of strain, and it's still flexible. I think I understood it correctly. I mean, I might be wrong, but I think that's how I get it. Yep.
Yeah, that's exactly how I thought of it. I'm really not an expert in this, but
oh yeah, neither am I.
Yeah,
cool.
But in this this picture, you can see how the titanium and the nickel are between the grains, and these are the martensite grains, which are harder, lot harder, and the titanium and the nickel, which are precipitated out, are in the austenite region, the softer one. So even in the band of the harder material, there's still austenite, the softer material, but there is a lot of martensite, and between the grains of martensite, which is really hard, there is titanium and nickel precipitation. Yeah, and in this picture you can see clearly see voids and imperfections in making process. So yeah, there's a lot of that throughout the making the process. Yes, here's another great picture of how it's how the titanium and the nickel are spread around in the material. They made a very nice graphic which shows it in the 3D. So yeah, that's really cool. In the method, they explain how they did it, but that's really over my head. I don't really understand how that's done. So yeah, back to the paper. What else? Yeah, this graph exactly shows what it's happening. Where the precipitation, the percentage of iron is very low at 6%. Most of it is nickel and titanium, and so on. Any questions?
I have. How is it ever compared in the paper how this material stands up to traditionally forge weld produced Damascus or other forged steel products? Because
no.
it's all well and being having like an additive manufacturing, but basis on how its mechanical properties stand up to forged, standard forged products. I don't know how strong these are relative to things like,
in the paper, they don't compare it to the standard manufacturing processes because I don't know. They just compare it in laser additive manufacturing sense.
Okay.
This type of alloy, which nickel and titanium, it's called. Have it highlighted somewhere here.
So I guess there's nothing in the paper that compares it to like a hand forged steel.
No, they just compare it to
boo.
standard print. Yeah, that's
Yeah, because what I'm interested is in how this material differs from a classically machined part. So if we're talking about a rocket nozzle, how does a rocket bell nozzle with the same size, dimensions, and spec of this material over one machine turned on a lathe and bored out the center and all that? How do those two? Because I've never had a PLA part ever be as strong as if an injection molded part of the same plastic and same weight and everything is.
yes, but you would tailor your product to your material. So if you're printing a rocket nozzle, you would make it with cooling channels and
That's the really
internal
cool
supports. But yeah, here they just compare it with no pause. So
okay. I'm going to try and have a look and see if there's any standardized samples, because I think we've got a couple books in the library that I can just pick up, and if we can find out what it is and find out, see how it does. So
another point I just remember, the alloy, it's called a miraging steel, which is the combination of martensitic and aging. The aging comes from a long heat treatment for the steel. So in classic manufacturing, if you're milling the miraging steel, which has very good material properties, when you machine it, you would have to put it in a furnace and temper it for quite a bit, for a long time. Let it heat up and let it cool down gradually, or that depends on the steel. But here they get the martensitic, the miraging type steel in situ, so there's no heat treatment necessary because they state in situ heat treatment, which is done by the laser. So as they're laying it and letting it cool, that's the aging part of miraging steel. So when you're making a miraging steel, you would have to age it normally, but here they just print it out and it's done. Any questions?
Not really a question, but I just wanted to add, due to the layering effects, there are now 5-axis laser printers now. So at that point, you can have the layers in basically any direction that you want.
Yes.
Which is going to be really, really interesting in the future.
Yes. Another interesting thing, they don't mention it here, but I wonder if you could, while you're printing it, since the material is carried by the gas, could you gradually change the material and the alloy that is being printed, so you could have a totally different type of alloy already welded. So alloy that is a lot more flexible, be it the one part of the part compared to the other. So
I mean, isn't that what they're already doing?
No, they're constantly using one type of alloy.
Yeah, because they're using the temperature changes. They are getting that effect.
Yes, they're just using temperature changes. I wonder if there's a process where they change the alloy mid-print. So that's the interesting part I want to know about more.
I believe there is. However, I believe the metal they were using was Inconel and something else. I can't remember what the other one was. And it was very, very weird and interesting.
Thank you. I'm trying to find out what the alloy is called. Thank you. It is Inconel?
Yeah, Inconel is used for high temperature, corrosion resistance, and where a lot of it is used in nuclear reactors, if I'm correct.
Having heard of machining Inconel, it sounds like an absolute pain in the ass because all of these are materials that are on my I don't want to machine in my life list.
So I'm pretty much done. I don't really. That's pretty much it for me. If anybody has anything to add, questions.
Come on, people! This is the time to ask about stuff. Be like, hey, I don't understand anything. Please help.
I don't understand why like you don't have like I've been trying to figure out the first uses of like this type of alloy and well, when you look at Damascus steel, like if you look up on the internet Damascus steel, like yeah, okay, it's pretty ancient, but when you think of like I've been trying to look at the history of using nickel as an alloy and using titanium as an alloy to additive like as an additive alloy to iron, and they don't mention the Damascus steel many places. Like it's
Yeah, that's
it's like it's been a secret for some time.
yeah. Damascus type properties are here just by layering. This alloy is a demaraging steel, and it's demaraging steel is hardened by the precipitates. Here, the precipitates
right.
are just caused by the temperature change, which cause it to be in the Damascus form.
Yeah, and
like in yeah, okay.
so mostly it really has to do with just a variety of different types of metals and carbon densities, and a lot of that just has to do with like the temperature and mechanical process originally. So like whenever if you like look into old school Damascus, you're usually looking at knives or swords. And they were just like, yes, we just took whatever crap we had and we just dumped it into a big pot. And then it turns out that when you take whatever crap you have and dump it into a big pot, it's better than just having one thing.
And originally, I think the folding process that is used in Damascus was used to draw out the impurities in the metal. So as you're folding it and hammering it down again, the scale contains impurities. So that was a big reason why the Japanese swords traditionally were folded so many times, because they had a lot of impurities in their iron. So to get a good blade, they had to fold it a lot. So that's the probable origins of Damascus, why it was started. Why did somebody do it? Because they were trying to make a better material by drawing in impurities out.
I don't know if you said this, but what was the benefit of using the gas feed for the powder than just having the powder in the bed?
I think it's greater control, since when you can have the part held in a 5-axis machine, so you can turn the head and start printing in a different way. When you're having a powdered bed, the part lays flat, and the sand is the material is spread over it. So you can't really just go turn it and start printing at a 90 degrees angle.
Wouldn't it also benefit if you need to change the heating of your material rapidly? A small amount on your part is going to be considerably easier to change the temperature of rather than a big old vat of powder.
Yes, exactly. And here, since they're using gas feed for the material, they can just stop the material and let the gas that carries the sand to cool it even more and faster.
Okay, so like as I just wanted to end with like I linked on the voice and video chat like in a space material database I actually found something which was heat dissipation and corrosion resistance, which led me to think, okay, those are the main reason why they might have kept it a secret for a long time. That like it doesn't corrode. Like you don't have like if it if you put it in water, it ain't gonna rust as fast as most others. And on top of that, like it's probably been used for satellites, which was probably part of keeping the secret, because space the space
It's
rigs
not
and
really
stuff.
a secret. It's just
Not a secret, but
obnoxiously
like,
complicated.
yeah, okay,
I
okay, yeah.
Yeah, which is different than
The,
being a secret. It just means you have to learn how to do a thing. Like
yeah,
people would
well,
become
uh,
journeyman and intern for like their entire life to learn how to make proper Damascus.
I
I mean,
have
it was
found
an
it.
amazing, yeah, it was an amazing article, because I didn't really find much about it.
Oh, sorry.
interesting thing about this alloy, which is a miraging steel, is they're used. This type of alloy is used to make enrichment turbines for uranium processes. So its export is regulated, and it's also used in skins of the rockets. So since it has good material properties at higher temperatures,
Right.
so yeah, it's regulated a bit. This
Yeah.
Right,
type of
right. You accelerate corrosion by having it heated up, and you also like have the nickel property of thermal dissipation. So you dissipate heat, and you also prevent like oxidation.
yeah.
All right. Can I clarify? Just this alloy has iron, titanium, and nickel. Those are the three properties,
Yes.
right? It's like three elements inside this steel. Is
Yes.
the yeah? Because I'm looking at the steel, just like the standard classical miraging steel. It's got the same properties like physical stress strain of a low grade miraging steel. It is no in any way up to higher standards of steel, but considering that it can outperform the lowest with those voids is quite literally astounding, because a lot of the voids do reliably reduce strength, because the grains can shift and move into those voids rather than having to so they can create
Yeah.
fractures and shear lines across them. That is,
Yeah. You
sorry,
get the voids only in the additive manufacturing, but
yeah,
Yeah.
if you use this type of steel in normal process, you have no voids, and it's
yeah.
probably a lot better.
A higher grade of this steel, let's just the grades, grade 200 is a tensile strength of megapascal of 1379. So the Damascus, the A sample does on average reach that. The B, the B, when they put it against the grain in B, it outperforms the lower grades considerably. Grade 2.5 is just 17,000 and some change. And 300, it goes to 2,000 megapascals, and it goes even up there with 350, which is 2,400 megapascals. So it's actually quite comparable, and especially in rocketry, where you would want a small amount of something that's strong rather than a large amount of something that is weak, because you have to deal with weight at every opportunity. This isn't terrible. It's
Yeah.
not great, but it's not bad
Oh,
either.
you can add up onto that alloy to have like perfect ablative properties. I figured, but yeah, like I ain't gonna talk too much about space, but yeah, it's awesome.
Yeah, and since the laser additive manufacturing, when we do go to space, Mars, the Moon, the manufacturing is probably going to be 3D metal printing. You're not going with the lathe to the Moon.
Oh, because right. Yeah, because you. Oh fuck, lathes heavy. Wow. Okay. Because yeah, how would you take a lathe to the moon? Because when things break, you need a lathe and a mill to fix things.
Well,
You
if
print
you're
the lathe.
producing steel on the moon, you probably have the capacity to ship it. But yeah, it's a lot simpler to just print out a beam, then bring a whole facility for rolling out the beams. So yeah.
Amazing.
So I'm done.
Yeah, I think somebody just tried to ask a question, but it just got all glitchy.
Uh-huh.
I was just saying, wow.
So yeah, that's the talk.
Thank you.
Yeah, thank you.
No problem.
Yeah, like I mean, the quality of that scientific paper is like top notch. I mean, whoa.
Yeah, I took it
Except
from
for
Nature
their
magazine. So.
except for their lack of control against actual Damascus. Like
That's
that
true,
really,
and they also
that really bummed me out. They're like, hey, this is really great compared to some crap that we made before. And it's like, cool, you made something, but like, how is it compared to like Japanese folded steel?
Yeah, I mean, like, yeah.
Yeah, but how do you reproduce it in the lab? You could
Buy it.
They could buy it. Yeah.
Yeah, I don't know how consistent are the.
Like, I mean, this is why I was pushing back against the like secret method. It's like when I lived in Florida, I was in a makerspace where a guy had a forge, and his whole thing was just taking random pieces of metal and turning it into Damascus. Like he would be like, "Yeah, I made this butcher knife. It's made out of like an old
Bike
saw
chains.
blade." Yeah,
Yeah.
like bike chains and stuff like that. So, like, it's you know, you can, I can, like, you want to get Damascus, I could totally go and get Damascus. I could get Damascus delivered to me on Amazon, like, tomorrow.
I did.
Okay, so
I've got a question about
someone had a question, but they couldn't get their mic to work properly. There's a phrase occurring in the interdendric regions. And then they use interdendric again. Can someone explain what interdendric means?
Dendric means between the grains. So the grains of martensite, where there is austenite, where the precipitation is happening. So yeah.
When you say precipitation, do you mean precipitation of the material, or is there a moisture? Like, be more specific here.
Precipitation of nickel and titanium. The nickel and titanium are precipitating and concentrating in the dendritic region.
Okay, so the solution, I don't know. Yeah,
it's kind of like if it's like the mortar between the bricks.
Yes.
Yeah. Only downside I would give the paper is, like, amongst other things, but the one thing that really made me kind of sad was the lack of conclusion. There is no conclusion. Like, the conclusion is basically pictures. So it's okay.
I've got a problem with this, and I've spent the past little while trying to solidify it. I've struggled when trying to find this alloy that they've created, which is just iron, titanium, and nickel. And I'm like, where's the Can somebody pronounce molybdenum? Oh fuck! I'm gonna put it in the chat because I can never.
Molybdenum.
Molly.
Where's the molly? Yeah, dude. If I'm gonna have my Damascus, I need my molly.
No, seriously. Most steels is like this. It's high moly, chrome moly steels. I'm like, where is the moly? What? I've searched the paper. There is no mention of moly in here at all, and they're not even covered like why is there no moly in this?
They my guess.
It's because they took it all.
No, like yeah, but it's rare. Like molybdenum is rare, but my wild guess would be that if you have like the right
steel production, it's
no, I know, but if you have the right concentration of nickel, if you know exactly how the denting, I forgot the word, but like the dissolution, like basically how to properly integrate both titanium and iron with the exact amount of nickel, then you kind of don't need the magnetic properties of molybdenum.
No, it's not. I'm trying to find out because molybdenum is one of the most prolifically used additives in high tensile strength steels. For a good example is anybody's kitchen knives who they are stainless steel with almost which are a high chrome moly mix steel.
Speak for yourself, dude.
Yeah, they are. The moly produces.
I'm using the carbon steel.
Yeah, they produce a hardness near carbon steel because of its moly content, and this disregards moly as not even a thing they've added into it. And I'm looking at ink now.
I think it's mostly a show off. They want to show off how well it blends with only those three.
So let's think about this from a structural standpoint as opposed to a chemical standpoint. And so in the same way, when we're talking about like NACA or all of this other material science type of things, we get down to this point where on a very small level, and by small I mean like micro or nano level, but the physical structure of the object changes the material properties. And so you don't need to add things because you can just change the shape of the thing, and the changing of the shape actually does the work.
Yes, and probably adding something more would interfere with the precipitation, which they probably desired the most.
Yeah, exactly. And that's the wood part, like the carbon part in steel, right? And I think the other way around with the molybdenum is because that, especially because when you make a sword, right, you have to hammer it to make it like enhance the compression strength and tighten the atoms together. I think that molybdenum is used because of when you increase magnetism in the compound, it will tend to aggregate more and so on. So yeah, it's a good point. They don't use molybdenum. They don't even mention it
in in tool steels like that. Most swords are made out because for once it's one subject I know about. Are most out of EN45 and EN333 or 303. They are quite low molybdenum steels because of the I don't know, wrong person to ask, but they want to be bendy. They want to bend way more before they then deform. Different strain stress diagram. They want a different characteristics. Moly is good because it's like putting it puts a lot of stress and it pre-strains the material, makes it hard in the way that it would be hard to walk if you're
right. But they don't even mention it. That's the thing. Like they either want to make it, they either want to prove a point, or they just want to cut down the cost. Or
it's because they want the simplest thing because this is research.
Yeah.
So you need the simplest thing, and on top of that, they don't need it because of the structural changes.
Yeah,
exactly.
And this is the whole point. It's like you don't have to do you don't have to find this material and then add it in. It's like you can use garbage. You can use anything. But like given the right pressures and shapes, it turns into something that is both flexible and strong. And all of this processing is secondary, actually.
I have found out why they didn't use molybdenum entirely. Gabe, you hit the nail on the head. They were trying to make an alloy in the characteristics of single crystal zinc alloys, which do not require or even wish to have molybdenum in it. I got sidetracked with Inconel and the margining steels. Right, they're trying to.
I mean, if you look up the Wikipedia on nickel, it's funny to see that apparently, like they postulate that many scientists disagree on the structure of nickel, which means it has like it. If you don't know much about it, you would not like if you know a thing that does the thing, as Gabriel says, you would not like mess with too much with the thing, else it doesn't do the thing anymore, kind of thing.
Yeah, it's basically alchemy. You're putting it in,
Yeah.
doesn't know what it is. So yeah, I wonder.
Yeah, to this day, it's still alchemy. Yeah.
Yes. I wonder what would be the material properties if you print the honeycomb structure out of this. So you have honeycomb Damascus steel. That'd be cool to see. But
Cool. Well, that was awesome. Thank you so much.
no problem.
Thank you very much.
Thanks, man.